Hello everybody, we're going to do a very introductory Taylor series video today. We're going to break down where the Taylor series comes from, the idea of it, and then we're going to show you the formula and do some quick problems. Okay, so before this unit, you should cover the series test. So you remember like the nth term test, geometric, alternating, you get it, right? So ... And you did a bunch of series tests for convergence and all that stuff. Now we're gonna continue that idea, but you'll see how it comes into play, not in this video, but in a power series video that's coming up. So you did this unit, and now we're going to kind of branch off a little bit again and think about the geometric series for a second. So if you recall that there's a geometric series from n equals 0 to n to infinity of, let's say, a times r, times r to the n. Yeah, let's just say that, right? I was going to give it in a specific form, but I think I'll do that in a different video. So in this case, we have our geometric series, and the condition was that this series converges if r, absolute r, is less than 1, and the sum is equal to a1 minus, or a, over 1 minus r, right? Really a1, but and yeah, so in this case, like, how can we extend this idea even further? Well, I'm going to choose, instead of putting r, I'm going to write x to the n. And to make it even simpler, I'm actually going to let a just equal to 1. So the infinite series of x to the n. This is a geometric series with r as x. So let's write the first few terms out. We have 1 plus x squared plus x cubed, and you get the idea, all the way to x to the n. Now, we recall, when does this series converge? Now we have a variable, so it's not like we don't know if it converges or diverges. We know an interval when it might converge. There's a certain number of values that'll satisfy this equation, right? So remember, so this is when absolute value of x, which is equal to r, is less than 1, it converges. Correct? And in this case, this is really just saying that x is between 1 and -1. This is what we call the interval of convergence, and we're going to get to that in a different video, not in this one. But this is just an introduction. But more importantly, let's remember what this sum formula was. Let's apply that here. According to that formula, the sum of this infinite polynomial, this infinite geometric series, should be 1 over 1 minus r, which is x. So that means that this entire series, or geometric series right here, is the same as 1 over 1 minus x? That's crazy, isn't it? And you can see, if you actually graphed it on Desmos as more terms are present, you'll see how it gets more accurate. And so, obviously for the interval of convergence. So yes, this is the idea of a Taylor series where we can apply, or we can say that certain functions that aren't really, this is not a polynomial on the right. This part I circled in blue, it's not really a polynomial, and it's really hard to calculate, like, what if x was like 0.3, right? It's kind of annoying. But we can now represent this function as an infinite polynomial. And that is the entire idea of a Taylor series, is that we can represent functions as polynomials. Okay? infinite polynomials. So here is Taylor's formula. Or theorem or whatever, but I'll say formula. So a function, let's say it's like, we'll say f of x, is equal to a Taylor polynomial of nth degree, which is also equal to f of a plus f prime of a times x minus a over a, or really, actually, sorry, not over a, 1 factorial, which is 1, plus f double prime of a times x minus a squared over 2 factorial, plus f triple prime of a times x minus a cubed over 3 factorial. And you can kind of see where this is going. This is really going to go all the way to the nth derivative of a times x minus a to the n over n factorial. So this is Taylor's formula. And what is this a, you might ask, right? That we kind of pulled this a out of nowhere. A is where the polynomial is the center. It's like where you're centering your Taylor series. So for example, and after we do a single problem with this, I'll show you what this means. Okay? So keep in mind with this formula, write it down as we solve the problems, and I'll bring it up briefly. But and by the way, this is really just a infinite sum from n equals 0 to infinity of f to the nth derivative of a times x minus a to the n all over n factorial. So yeah. Now let's apply this formula to a function e to the x. So let's say that e to the x, and we want to do it for centered at 0. Okay? And that is essentially saying that a is 0 in the formula. So let's do it. So remember, the Taylor polynomial of nth degree, and let's go to the third degree. Okay? So to the third degree. That means when it says centered at 0, that means a is 0. And when it says third degree, it's really just saying that take it until you get to the third derivative. So remember, the Taylor formula, it was f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a x minus a cubed over 3 factorial. Okay, so this is this is to the third degree, right? We have our third derivative. Okay, so we're going to stop here. So what do we need to find? We need to find f of a, which is f of 0. So we need to find f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So first, let's find out what f prime is. So we know f, so f of x equals e to the x, right? So f of 0 will just be 1. F prime of x is also equal to e to the x, and f double prime of x is also equal to e to the x, and so is f triple prime of x. So e to the x, obviously having its unique condition that its derivative is itself, makes this problem very easy. And of course, that means that every single one of these are just 1. So let's plug it in to the formula. So remember, we have f of a, which is 1, so it's going to be, so e to the x is approximately the Taylor polynomial to the third degree, which is equal to 1 plus 1 times x minus 0 plus 1 times x minus 0 squared over 2 factorial plus 1 times x minus 0 cubed over 3 factorial. Now, this obviously I wrote the 0 out just to make it, very detailed, but this is really just 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Cool. So this is your answer to this problem. Now, if it asked you, okay, what about the nth degree? Well, you can notice a pattern here about what's going to happen. Notice how it's just going to be like this, right? You can see a pattern. 1 plus x squared over 2 factorial plus x cubed over 3, x to the 4th over 4 factorial plus x to the 5th over 5 factorial, and you can notice that this pattern is going to continue. Why? Well, because e to the x has the same derivatives. You can take it infinitely many times. So that means that this eventually is going to the nth degree, which is going to be x to the n over n factorial. And in fact, e to the x, the actual Taylor series summation, is the infinite sum from n equals 0 to infinity of x to the n over n factorial. So there is your Taylor series for e to the x. And that is, it's mind-blowing. Now, what does this actually, what does this centered at 0 mean? Because we still haven't figured that out. So this is what's happening. So e to the x kind of looks like this, right? Now, when we say centered at 0, we mean that the polynomial approximation, right? So we start at 1 plus x, right? So it's going to be x like this. Then it's going to be plus x squared, right? So then we're going to get rid of this line, and it's going to be like something like this. Then it's going to be plus x cubed, which is going to be like something like this, or whatever. Then it's going to be x to the 4th, which is going to be like this. Then it's going to be x to the 5th, which is going to be like this. Then it's going to be x to the 6th. Oh, by the way, over 2 factorial, over 3 factorial, 4 factorial, over 5 factorial, over 6 factorial. Sorry about that. And it's going to be like, and as you get further and further, more terms of the Taylor series, you're going to get closer and closer to the actual function itself, right? And there's great visualizations out there, a lot of great YouTube shorts with animations that do this, so check one out. And what's happening is we're centering this at 0. This would be different if we started to center it up here. Then our first approximation would start like this, then we go like this, then we go like that, then we go, again and again and again. So that's what it's saying, that it's centered at 0. That means it's gonna start from 0, and its approximations are gonna be correct when it's near 0 at the beginning. So it's gonna start from here, and as you branch more terms out, it's gonna start getting closer and closer to the actual function from 0. Okay? So from there, let's find a Taylor series approximation for sine of x, right? And we're going to say it's centered at 0, comma 0, let's say, more specifically. And let's go to the 4th degree. Okay, so we need to obviously say, okay, so f of x equals sine x. And by the way, When we say that the Taylor series is centered at 0 specifically, this is called a Maclaurin series. Specifically when it's centered at 0. Okay, so let's continue. So f of x equals sine x. So we need to find the fourth degree, so up to the fourth derivative. So f prime of x is equal to cosine x, f double prime, negative sine, f triple prime, negative cos, and f quadruple prime, we will be back to our sine x. So f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime of 0 is negative 1, and f quadruple prime of 0 is 0. And this was going to look interesting. So with the formula, remember, it's f of a plus f prime of a x minus a over 1. So really not really over anything. Plus f double prime of a x minus a squared over 2 factorial and dot dot dot. You get it. So our Taylor polynomial is going to be 0 plus 1 times x minus 0, so x, plus 0 times x minus a squared over 2 factorial, which is entirely just 0, minus 1 times x minus 0, which is just x, cubed, sorry, this is 0, so this is really just x squared, over 3 factorial plus 0 times x to the 4th over 4 factorial and dot dot dot. Now, look what's going on here. First term cancels out, third term cancels out, fifth term cancels out. And if you notice a pattern here, it's going to be just, so we're saying that sine x is approximately just x minus x cubed over 3 factorial. Now, if we went to the next term, it's going to turn out to be plus x to the 5th over 5 factorial. The two terms after that, it's going to be minus x to the 7th over 7 factorial, and dot dot dot. Okay, so why is this true? Well, for example, the Maclaurin series at 0, every other term has a derivative at 0 of 0, right? Derivative of sine is 0, and sine, cosine, sine, cosine, cosine, sine, cosine, sine, cosine, it's going to alternate constantly. So every even term, in fact, more specifically, you can see the 0th derivative, 2nd, 4th, is going to result in 0. Another interesting thing is, look, the signs are alternating. Look at this, x minus, then plus, then minus. So that's really important. And look at the degrees. They're all odd. And what is sine? Sine is an odd function. So you see how very connected everything really is. And thus, the actual sine Taylor series is the infinite sum from n equals 0 to infinity of x to the 2n plus 1 over, I'm pretty sure it's just n factorial. Oh, 2n plus 1 factorial, sorry. Okay. So that's it. So that's insane. And guess what? We're not going to derive it, but cosine is going to look like this. And this is insane, right? Because it's still alternating, but the powers are now even, and cosine is an even function. And in fact, its Taylor series can be represented as the infinite sum of, it's going to be x to the 2n over 2n all of that factorial. So there you have it. This is a basic introduction to the Taylor series where we can represent sine x and other functions like, e to the x, sine x, cosine x, tangent x, whatever, as infinite polynomials. And why is this important? Well, think about how does a calculator evaluate something like this? Cosine of 31 degrees. How do you do this? There's no, what is that? And from here, it's really important to notice that, okay, so this is how calculators are doing, their calculations. They're actually putting, 1 minus 31 squared over 2 factorial plus 31. They're actually putting in these values, which is really important. Actually, sorry, it's not 31 they're putting in, it's actually the radian version. So 31 degrees, I'll say, squared over 2 factorial plus 31 degrees to the 4th over 4 factorial and dot dot dot. They're actually putting it into polynomials and making direct and accurate approximations from there to give you your solution. So in fact, all the calculators are actually using Taylor series to give you those non-rational inputs, or those inputs that just don't really, they got a lot of decimals and all that stuff. So this is an introduction to Taylor series, and in fact, there's something really cool about this series that we can use to derive some really insane stuff. So yeah, stay tuned. There's a really great animation video that's coming up about Taylor series, and yeah, hope you guys enjoyed this video. See you in the next one.